Yeah, thanks for putting up this event. Thanks everyone for being here in the session. You already heard the title and who I was with. Alejandro Moreo and Fabrizio Sebastiani were my hosts at the CNR in March, where I visited them. And the goal of this work was to estimate the prevalence of classes. So how often each class appears in an unlabeled set of data or in multiple such sets. This estimation of class prevalences is also known under the name of quantification. We will also have another talk in this session by Pablo Gonzalez. And here the twist is that we want to estimate the prevalence of ordinal classes, of classes over which a total order is defined. In principle, any quantification task can be approached by just classifying each individual instance and then counting how often each class has been predicted. However, this so-called classify and count method is well known to be insufficient under the presence of prior probability shift. So if the probability of the classes changes between testing and training, then your classifier will be biased towards the class prevalences it has seen during training, and therefore we can not just use this classifier to solve the task of quantification. Therefore, a whole zoo of thousands of other methods has emerged. Of course, I'm a bit exaggerating here, but it's many, many methods. There's a huge body of literature that deals with this problem. To give you a rough idea of how these methods might work, we can have a look at a binary case. Adjusted classify and count is one of the most classic, most basic methods. Here we counteract these biases of the classifier by first classifying and counting how often each class is in the sample. And then we have to subtract the false positive rate of the classifier and divide by the difference between true positive rate and false positive rate. So these rates can be estimated on training data. So here we have a very simple way of adjusting what a classifier would return. And this adjusted classify and count method is already Fisher consistent, which means that it will return the right answer if you would have an unlimited amount of data. However, it might exhibit some variance. It might also, if you have very small data sets, produce answers that are larger than 1 or lower than 0, so not even a valid probability. And this is the reason why we have all of these other methods which also solve problems like this. So another aspect of quantification is that you need to also evaluate in a different way than classification. Here you have to have multiple sets of data over which you evaluate. Therefore, you would, for instance, divide into training items to learn a basic classifier, for instance, or another representations from which you can do the quantification later on. And then you can sample sets of data for validation and sets of data for testing. And here we have multiple different experimental protocols that we can use to produce the samples, with different prior probability shifts. So if there's one thing that you should take home from my presentation here, is that quantification is a task that has to be handled as a task in its own right. You cannot just use a classifier. You have a huge body of literature that is concerned with methods for solving this issue. Now, what does ordinality mean? Ordinality means that the classes are totally ordered. Like, for example, in product reviews, you might have a sentiment expressed in a star rating, and 5 stars are better than 4 stars, which are better than 3 stars, and so on. So your classes are ordered. Therefore, you also have this quantification task often in sentiment analysis. Also in our experiments, we have covered a natural language processing task where you want to estimate the sentiment, but not the sentiment of each individual review, but the sentiment over a set of product reviews. This would be akin to wanting to know what the overall sentiment towards a product is, rather than wanting to know what the sentiment of each individual customer is, because we might want to improve our product as a whole. However, I come from a very different area. Although I'm a computer scientist, I'm working mostly with data that astroparticle physicists provide me with. This is data by a telescope of this kind. We are interested here in properties of particles that we can measure. And what we ultimately want to have, so first of all, we need to predict the properties of the particles, but then we are interested in not in the properties of each individual particle, but in the properties of an entire set of particles that we have measured. Like this one, this plot is called an energy spectrum. Here on the x-axis, we have the energy of the particles that we are interested in. And on the y-axis, we have the flux. This is a physical domain-specific quantity, but this is directly proportional to the probability. And when we have a bar plot, like in this unfolding result, then we have different energy classes. So for each particle, we can predict the bin in which the energy bin in which each particle falls. And we are interested in the probability of these bins that we predict as classes over an entire set of data. So in fact, we have an ordinal quantification problem in astroparticle physics, but not only here, we also have it like in product reviews and in sentiment quantification. Our idea in addressing this ordinality is to introduce a regularizer. Most methods of the that already exist, they would minimize a loss function in order to find a probability vector, a vector of class probabilities that is most likely to have produced the unlabeled sample. And here we are now adding a regularizer to this loss term, which expresses our assumptions about ordinal solutions. And these assumptions are essentially that neighboring classes should not differ too much. This is a very natural assumption in ordinal classification in general, where you would assume that neighboring classes are similar to some degree. Here we make this assumption very precise in requiring that neighboring classes should be similar in terms of their class prevalences, in terms of their class probabilities. And in fact, this idea is not even new. This is something that physicists have proposed already in the 80s. However, they call quantification or supervised class prevalence estimation, they call it unfolding, which has prevented the two research communities from computer science and from astroparticle physics from drawing connections to. It has prevented them from seeing that mathematically speaking, what they solve is essentially the same problem. And part of our contribution is to unify the methods from the physics literature and from computer science literature in a common framework that characterizes algorithms from both fields in terms of a loss function, in terms of a regularizer, and in terms of a feature transformation. And we can reuse this regularization terms from physics also in computer science to address problems like, for example, sentiment quantification on text. Yeah, this is just to show you we have many different methods covered here. In each row there's one method, and they are characterized in terms of loss functions, regularizers, and feature transformation. You don't need to grasp the details, just recognize that the computer science methods, they all do not use any regularizer, but here in the first block, the physics methods, they do. And our proposal is just to reuse this regularizer and plug it into the existing loss function and feature transformations that have been proposed in computer science. Also, the evaluation should be changed for ordinal tasks, but only slightly, because what we want to test is not against any type of prior probability shift, but only those that might also naturally appear in ordinal quantification. Let's take a look maybe at these results. Here we have one experiment on the telescope data in 3 different experiments, 3 different experimental protocols in the columns here. And in the rows, we have all of these methods. In the first block, we have physics methods, then we have computer science methods, then we have physics methods that we have improved, and we have our new methods, which are the ordinal counterparts of the existing computer science methods. And we see that all these improved versions, which take ordinality seriously, they outperform the competition in all of these 3 experimental protocols, which test for different properties, so to say, of the algorithms. So to wrap it up, our goal was to predict the prevalence of each class, of each ordinal class in a set of unlabeled data or in multiple such sets. We have seen that we cannot just address this task by classifying and then counting how often each class is predicted, but we need dedicated methods to solve this. And our approach for ordinal quantification in particular was to introduce a regularization function that expresses our prior assumptions about ordinal likely solutions. We have software that has these features implemented. We also have published the data sets that we use for evaluation, which are very extensive, very large volume data sets. Yeah, so feel free to play with them whenever you stumble upon a task where you are not interested in each individual classification outcome, but into the prevalence of classes in your unlabeled sets of data. Thanks.